Okay, today we start the chapter 15, the last chapter of our textbook, Vector Calculus. First section, Vector Differentiation. Okay, in this chapter we study vector calculus on vector field. Okay. And Green's theorem, Stokes theorem, and divergence theorem, and Rhine integrals, and those are the major topics in this chapter. Okay, first section, vector differentiation. Let D be a subset of R2 or R3. A scalar field on D is a scalar valued function, f of x, that assigns to each point, x and y, or x, y, z, in D. So any user real valued function on D is a scalar field. Scalar field, okay, and for example, a function f given by this, f of x, y is equal to x plus y. This is an example of a scalar field defined on R2. Okay? F of x, y, z, which is x squared plus y squared plus g squared, is also a scalar field defined on R3. This scalar field can be called a scalar function as well, because this is a scalar. We start from the vector, the domain in R2 or R3, but the output is a scalar like this. So we call it's a scalar field or a scalar function. This is an example of a scalar field, a scalar function, such as temperature or pressure can be represented in this way. And x and y, we can define a number that represents the color, like this. Next, let D be a subset of R2 or R3. A vector field on D is a function f that assigns to each point x, y in D a 2 or 3-dimensional vector f of x, y, f of x, y. So, f of x, so here's the example. This is a vector field is defined. So this is the example. F of x, y, the image is m of x, y times the vector I plus n of x, y times vector j, where m and n are scalar function of two variables, and I and j are unit vectors along the coordinate axis. These are scalar functions from here. Scalar functions are called component function of this vector field. Okay, these are the vector example of vector field on a sphere. Okay, the domain is in R3. And the range is a vector. Here also, domain is in R2 here, and the image is a vector like this. Okay, these are the examples of scalar field and scalar the vector field. Okay, let's draw a vector field on R2 defined by f of x, y is like this. Okay. This is the graph of this function. As you see, what it means is at the point 1 and 1, we have what? 1/2 I plus j. That means at 1 and 1 at this point, we are having a vector on the I direction of half and y direction to 1, like this. So this represents this vector at point 1 and 1. At 0, 0, we have a 0, 0 vector here. And at -1 and -2 and 1, then we have, when x is equal to -2 and y is equal to 1, we have 1 and 1 vector, like this. So this exactly represents this vector field, isn't it? Okay, here just, lengths of the vectors are like this, and vector point roughly away from the origin, and the vector farther from the origin are longer. It's a bigger. We can examine that in here. Vector, as you see, this is the vector field of this function that you have seen. Vector field of 1/2 x I plus yj. That vector can be represented in this way, the coordinate form. And these are the vector form. It's in the near the origin, it has the length is small. As far as it goes far, that the length of the vectors are getting bigger and bigger, isn't it? If we change the vector like 5, like this, then we will have a different vector field like this. If we change it as not like this, minus 20 to plus 20, or you change it to 23 to 23, then we will have another function like this. Okay. As you see, it moves 5 times far from compared to the x-axis. That shows the directions are much. It's into the x-axis direction, the x-axis direction. If you change it to here as 120, it's like star. Yeah, times like this, then we will have a totally different vector like this, isn't it? So it goes when x goes in 1, x goes 1, then y goes to 120. So that's at each point we have the vector directions on the y-axis like this. Okay. So this is so all you have to do is just plot vector field of this function. X-axis 1/2 x and y-axis and it's a y, and from -3 to 3 and -3 to 3. That gives us this. Okay. Next example. Draw the vector field on R2 defined by f of x, y like this. And y and x, not x and y. Yeah? With this. Then the length of this vector is always 1 because it's a normalized. The length is always 1. So as you see, the vectors are all, the length of the vectors at every point is 1. Isn't it? Okay. And only the directions. And x and y is opposite. So when x and y is equal 1 and 1, then 1 and 1, then you have 1 and 1, then you have a direction to 1 to 1, like exactly like this. If it's 2 and 1, then at 2 and 1, you have a direction like this. When it goes to 1 and it goes to 2, like this, with normalized by this his length. So this also can be done at the same code. All you have to do is just plug this function in the code that you have seen to draw these pictures. Actually, that's what I draw this one. Okay, draw the vector field of 3 variables like this. Draw the vector field on R3 defined by f of x, y, g is equal to minus yk. So I part is 0, j part is 0, and only k part is left. So it's on the g-axis. Okay? So what happened? When x, y, g is equal to are all 1, and then we have what? Minus 1k. So when x is equal to 1 and y is equal to 1 and g is equal to minus 1, like this, isn't it? When g is equal to 1, when g is equal to 1, and the direction is what? Minus 1k. It's on the down direction. Let's see. So we plot the vector field of 3 variable function, and here ijk. So we have, this is different. We should have 0, 0, minus y. Isn't it? Okay, then we have from this direction. Okay, let's see. We should have, in order to have the right one, ijk. So we should have 0 here and minus y. 고쳐줘요. 그치? 이 행군 고쳐놓으세요. 코드가. Okay, because ijk and in the front we have minus y like this. Then, okay, we may have to change it. Okay, this is the 3-dimensional vector field that we see, that we can draw. If we have, in before we have this like this. It's different. So 여기서 어떻게 고쳐야 되냐? So yeah, we have seen how this graph works. Next, gradient vector field. This is another example of a vector field. Okay, if f is a scalar function of 2 variables, then the gradient of f, this denoted by gradient of f or delta f, is defined by the vector like this. The first derivative of f with respect to x times I plus the first derivative of f with respect to y times j. If we have a three-variable function, then the gradient of that function is like this: fx I plus fy j plus fj k, like this. Okay. Okay. Therefore, the gradient f is a vector field in R2 or R3, and it is called a gradient vector field. Gradient vector field. This is a contour map and gradient vector field of f of x, y is equal to x squared plus y squared. Okay. This all this red direction shows the what? Shows the directions, the vectors of the gradient of two variable function x squared plus y squared. So let's see the example. Find the gradient vector field of f of x, y, which is x squared minus y squared, and draw the gradient f of f together with the level curves of f. Okay, how they are related. Okay, here. We define a function x squared minus y squared as f, and print the gradient of x gradient first, then plot vector field of that gradient. So now this command allow us to draw the gradient vector field. Let's see how it is. Okay. This is the gradient vector. Actually, I didn't draw the contours of this function together, but you know how to do it. But anyway, this shows the gradient vector field of this function, x squared minus y squared. Okay. But as you see from this graph shows, the gradient vector field and the contours, you see? And these are the level curve of a contour. Level curve. How it is related? How? 이인행군. 김유정 양. 자, 요 벡터하고 요 컨투어 라인하고 요 레벨 커브하고 어떻게 관계가 돼 있어요? 다 각각 보면 다 직교인 걸 볼 수 있죠. 올소거나. So as you see from as you observe from the level surface, level curves and the vector field, then this gradient vector and that level curves, the slopes are orthogonal. So gradient is perpendicular to the level curves. This example shows that fact. Next thing is a line integral. You know, you wanna find the length of a curve. So this is the way to do it. Let f be a continuous function defined on okay, let's do it later. Okay, any question on section 15.1 first? Okay, then we'll continue on 15.2.